Okay, so we're now looking at question 3 of the end of unit assessment. So what we've got here is a cell with some internal resistance R with an EMF of 9.0 volts. And we've got it connected across these two resistors in parallel, and then those are in series with this 6 ohm resistor. So we've got the current going through the battery, and we know that it is 1.0 amps going around here. And he wants us to calculate the potential difference between points A and B. So if we want to calculate potential difference, we need to first know what the resistance between A and B is. So 1 over the total resistance is going to be 1 over 2 plus 1 over 2, which is equal to 1, which means that the total resistance is going to be 1.0 ohms. Now, V between those points is going to be the current between those points multiplied by the resistance, which is 1 times 1, so that's going to be 1.0 volts between them, giving us an appropriate number of significant figures. Okay, so then in terms of using that to calculate your internal resistance, so we've got 1 volt between A and B, so let's first calculate the potential difference across the 6.0 ohm resistor. So that's going to be IR, so that's going to be 1 times 6, which is going to be 6 volts. So that means that the potential difference across R is going to be 9 minus 6 minus 1, which is 2 volts. So that's the potential difference across R. So if we want to know the resistance of R, we're going to need the potential difference across R divided by the current, which would be 2 divided by 1, which gives you 2.0. So you're going to get 2.0 ohms as your internal resistance there. Again, just using Ohm's law, as is often the case for these electricity questions. Scroll on. So we want to calculate the total energy transformed by the battery in 5 minutes. So first of all, we need to think about how you calculate the power. So power is IV. So that's going to be 1 times by 9 gives you 9 watts. Now energy is power times by time. It's going to be 9 times 5 times 60, which is going to give you 2700 joules of energy there. Okay. So we want to calculate the percentage of energy that's dissipated by inside battery. So you see here it's dissipated in the battery rather than outside the battery. So in the battery, remember we had a potential difference of 2 and the current is 1, so we're going to get 2 watts, which over 5 minutes, so the energy dissipated in R is going to be 2 times by 5 times by 60, which gives you 600 watts. So we need that as a fraction of the whole. So the percentage is going to be 600 divided by 2700, which is the total, times by 100, and that gives you an answer of 0.22 times 100, which gives you 22%. The key thing, this and the thing most people find difficult, is actually working out what it's talking about. So it's the energy dissipated inside the battery as a fraction. That's why you have that 600, and then you can convert to this part here. So let's move on to the next. So then it's asking, well, why might it be an advantage for a rechargeable battery like this to have a low internal resistance? And there's a few different things. So low internal resistance means that you have low total resistance in your circuit, which means you have a high current. And so the advantage of this, so this is explaining it, but that means you're going to have faster charging. So if you have a higher current and you need to charge your battery, having a higher current will allow you to charge your battery faster. Another thing you could think about is if your I, so if we talk about your R is decreased, that means the energy lost across R is going to go down, which means you have a more efficient or less wasted system there. If you have this, and then this is sort of trying to explain how that works. If you have a smaller resistance, there's going to be a lower amount of energy transferred as heat by that internal resistor, so then that's going to result in a more efficient charging setup.